Hello friends, in this video I will discuss the electric potential and the curl of E, electric potential and related problems, and potential and electric field due to electric dipole. And to find electric field is little bit difficult in case of 1 upon 4 pi epsilon naught dq by r square into r cap, because r cap is a vector and sometimes it is difficult to use the integral for a vector or unit vector. So to find the electric potential is easier, because in case of the potential we have 1 upon 4 pi epsilon naught dq by r, so there is no r cap or r vector is there, and if we can find out the electric potential, then we can easily find out the electric field using the negative gradient of potential. So this is in some cases we will find the electric potential first and then the electric field. And now we will find the curl of E. Suppose we take the simplest example. A point charge is there and the electric field due to the point charge is 1 upon 4 pi epsilon naught q by r square in r cap direction, and the line integral of this field from a point A to B. If we see in this figure, we have point A is there and point B is there, and the path is going like this. So the line integral of this field will be E dot dl, and the path is from A to B and points A to B. And in spherical polar coordinates, we have the dl vector is d r cap plus r d theta cap plus r sin theta d phi cap. So E dot dl will be, E is this and dl is this, so only r cap dot r cap will give us this value, other terms will be 0. So E dot dl will be 1 upon 4 pi epsilon naught q by r square into dr. And now we have A to B E dot dl 1 upon 4 pi epsilon naught A to B q by r square dr. If we put the value here, and then 1 upon 4 pi epsilon naught q by ra minus q by rb. If you integrate 1 upon r square, it will be minus 1 upon r, and if you put the limits a to b, then it will 1 upon ra minus 1 upon rb. And for a closed path, we have, if for a closed path E dot dl is always 0. But using the Stokes law or Stokes theorem, we can change the line integral into surface integral. Line integral E dot dl can be written as del cross E dA. So this E will become del cross E. So if we compare these equation, then del cross E should be 0, because E dot dl equal to 0, so it means del cross E should be 0. So this shows that curl of the electric field is 0, and that's why electric field is irrotational. And in some cases you have to find that if some vector is valid electric field or not, then you will have to test the del cross E should be 0 for that vector, then it will be only a valid electric field. Now we will discuss the electric potential. And electric field is a vector function whose curl is 0. We have seen in last slide del cross E equal to 0. And if the curl of any vector is 0, then it is equivalent to gradient of some scalar. So this was the Helmholtz theorem. And here we want to transform this vector function E to a scalar function. Because the line integral is independent of path, we can define the vector, define a function v like this: v equal to minus E dl, and from a reference point O to R, and this scripted R, scripted O here, scripted O is a reference point, and B depends on the point R. So it is called the electric potential. It is the work required to take any unit charge from reference point O to the point R. And the difference between 2 points A and B can be written as BB minus BA equal to BB means O to B EDL minus O to A EDL, it will be plus, and if we rearrange the term minus O to B E dot dl, and if we change the limits O to A now A to O, then it will be E dot dl, and using the property of definite integral it will be minus A to B E dot dl. And fundamental theorem on gradients says that if we have A to B E dot dl, it can be written as del dot B dot dl, and if these two integrals are the integrand should be also equal, because both are the line integral dot dl, so E should be equivalent to minus del V, E equal to minus del V. So this is how we can find out the electric field. We can relate the electric field and electric potential, and potential is defined as potential difference between 2 points BB minus BA equal to minus A to B E dot dl, and the unit of potential is volt or Newton meter per coulomb or joule per coulomb. And when we want to get the potential V, so if the Gauss law is useful, then it is easy to find out the E, and then we will take the E dot dl, and the potential is some reference point to P E dot dl. But if we cannot find the electric field easily, then we will have to use the formula, the simple general formula 1 upon 4 pi epsilon naught integral dq by r, and this may be different charge distribution. Suppose dq equal to lambda dl for the line charge, for surface charge sigma dA, and for volume charge distribution rho d tau. So this is how we can find out the potential. Now we will discuss a simple question to understand how we can find out the potential, and using this potential how we can find out the electric field. So if we have a straight line segment of length 2L, and we have to find the electric field at point P at z distance from this wire, and it is carrying the uniform line charge lambda. So first we have to find the electric potential, and then also to find the electric field. So electric field can be found by negative gradient of the potential. So we will see that if we take a small line element on this wire in y direction, and at distance from this center to y, a small element dy is there, and at a point P we have to find out the electric field due to or the potential due to this small line charge. So dq will be lambda into dl, and dl in y direction, so we will take dl as dy. So dq equal to lambda into dy. So the dv will be 1 upon 4 pi epsilon naught dq by r, and r equal to this distance r equal to this z square plus y square in this right angle triangle, z square plus y square, or y square under root y square plus z square. This is r. So dB equal to 1 upon 4 pi epsilon naught dq by r, and dB equal to 1 upon 4 pi epsilon naught dq can be written as lambda dy divided by r means under root y square plus z square. This is question number 5. And if we integrate this equation, and left hand side will be dv, integral dv, and here lambda by 4 pi epsilon naught, this is constant taken out, and the limit from minus L to plus L if we integrate for the whole wire, and dy by under root y square plus z square. So this can be written as, because if we replace y with minus y, then it will give us the y square term is there, so it is a even function. So we can minus a to a fx can be written as 2 times 0 to a fx for the even function. So we have written it 2 times lambda by 4 pi epsilon naught, and the limit minus L to L which change 0 to L we have put 2 here, dy y under root y square plus z square, and this is a standard integral, and the integral of this kind of standard integral is lambda by 2 pi epsilon naught, this is constant, log of natural log of y plus under root y square plus z square, and limit is 0 to L. And if we put the limit lambda by 2 pi epsilon naught log L y L plus L square plus z square by z. So this is the potential, and now we can find out the electric field also using the negative gradient of this potential V, E equal to minus del V, and here this V is function of only z, so we will take minus delta V by delta z in z cap direction, because there is no x and y term, so we will have to differentiate it with respect to z, and finally we will get this kind of expression. If you do it by division or by product of two functions, then you will find the differentiation of this. So E equal to 2L lambda by 4 pi epsilon naught 1 upon z under root z square plus L square in z cap direction. So this is how we can find out the electric field using first calculating the B. We have calculated B here, and then from B we have found the electric field using the negative gradient of this potential. Now another example is for a loop, circular loop of radius capital R. We have to find out the electric potential at point P, which is at z distance from the center. So this loop is in xy plane, and we have to find out at a distance z, at height z, we have to find out the electric field. So the coordinates are 0, 0, z for this point P, where we have to find out the potential. So again we will take a very small line element on this circumference of this loop, and this dl equal to r into d phi. For a very small angle d phi, this arc dl equal to r into d phi. R is the radius of this loop, and now we have to again write the formula for potential. V equal to 1 upon 4 pi epsilon naught dq by r, and 1 upon 4 pi epsilon naught dq by under root, this r is z square plus this right angle triangle in 3 dimensions. We can see z square plus capital R square equal to this r. So under root r square plus z square, this distance is here, and because this is changing from 0 to phi is 0 to 2 pi, so we will take the limit 0 to 2 pi for the phi. So dq can be written as lambda into dl, and lambda into dl equal to r d phi divided by r square plus z square, and now we have to integrate it. So lambda r, this can be taken out, so only integral is d phi 0 to 2 pi, so it will give us 2 pi, and 1 upon 4 pi epsilon naught lambda r by under r square plus z square, and 2 pi will be cancelled out, lambda r by 2 epsilon naught 1 upon under root r square plus z square. So this is the potential at a point P due to this circular loop which have a uniform line charge density lambda. Now we will discuss the potential and electric field due to a electric dipole. And electric dipole is consist of two equal and opposite charges plus q and minus q at a very small distance d, and we have to find the potential at a point P, which is at a distance r from the center of the dipole. The center of the dipole, the length was d, so d by 2 here is the center, and we have to find out the potential and then electric field. So if this angle is theta, then this lower angle will be pi minus theta or 180 minus theta, and this distance from plus q is r plus is the distance from plus q, and r minus is the distance from minus q of this point P, where we have to find out the potential. And the potential due to this is 1 upon 4 pi epsilon naught q by r plus minus q by r minus. But we don't know the r plus and r minus. We have only the distance. We know the r and the distance d. So we have to use this r plus and r minus in terms of d, theta and r. We then using some trigonometry or using the law of cosines. So r plus and r minus can be found by law of cosines, and cosine law is if we have a triangle with sides a, b and c, and if this angle is alpha between b and c, then this side, one of the side a square can be written as b square plus c square minus 2bc cos alpha. So this is known as the law of cosines for a triangle. Now we can find out for these two triangles. One is this one with r plus r and d by 2. These three are the sides and one angle is theta. So for this we can write this law: r plus square equal to r square plus d by 2 square minus 2 r into d by 2 cos theta, and 2 and d by 2 this will cancelled out, minus rd cos theta. So this one is for this above triangle, and other triangle will give us r minus square equal to r square plus d by 2 square minus rd cos pi minus theta. Angle is here, pi minus theta is there. So r square plus d by 2 square plus it will be cos pi minus theta is equal to minus cos theta. So rd cos theta is, sign is plus here. So little bit we will rearrange these terms. Take the r square common in this equation 2 and 3. R square plus r positive square equal to r square 1 minus d by r cos theta plus d square by 4 r square, equation number 4, and r negative square equal to r square common 1 plus d by r cos theta plus d square by 4 r square. This is equation number 5. And because r is much greater than d, so d square by 4 r square is very small number and it can be neglected. So d square by 4 r square, it can be neglected. Now we have 1 upon r plus equal to 1 upon r 1 minus d by r cos theta. So we will take the, because 1 upon r plus, so we will, it will be under root of this, so minus 1 by 2 power. Similarly r minus will be under root of this, and 1 upon r minus will be 1 upon r 1 plus d by r cos theta to the power minus half. And now we will have to expand these using the binomial theorem, and finally we will have get the 1 upon r plus minus 1 upon r minus, and finally we will find the potential. So let's solve it using the binomial theorem. Binomial expansion is if 1 plus x to the power n can be expanded as 1 plus nx plus n into n minus 1 by factorial 2x square plus n into n minus 1 n minus 2 by factorial 3x cube. So this is the binomial expansion. But for very small values of x, we can write 1 plus x to the power n equal to 1 plus nx, and higher order terms will be neglected because this x is small, so x square, x cube, x4, these all terms can be, higher order terms can be neglected. So now we will have 1 upon r plus can be written as 1 upon r, 1 plus d by r was there, so minus 1 by 2 will be here, so it will be d plus d by 2r cos theta. Similarly 1 upon 1 r minus equal to 1 upon r 1 minus d by 2r cos theta. In last slide you have seen the power was minus half was here and plus half was here, so we have used this expansion. 1 plus x to the power n was 1 by 2 or minus 1 by 2 in this case. So if we subtract this 1 upon r minus r plus minus 1 upon r minus 8 minus 9, so it will be 1 upon r 2d cos theta by 2r or d cos theta by r square. And if you put this equation number 10 in the equation number 1, then we have b equal to 1 upon 4 pi epsilon naught q d cos theta by r square, and q into d can be written as p, which is the electric dipole moment. So 1 upon 4 pi epsilon naught p cos theta by r square. So this is the electric potential for the electric dipole. And using this potential, we can also find out the electric field by differentiating this function or taking the gradient. So the electric field can be found by negative gradient of potential. E vector equal to minus del B. So del will operate this function, and this function was containing r and theta, so we will have to use del in spherical polar coordinates, and E was minus delta V by delta r in r cap direction minus delta V by delta theta 1 upon r in theta cap direction. Phi cap term is not in that expression, so E phi will be 0. So we will have the electric field as ER in r cap plus E theta theta cap direction. So we will have to find out the differentiation. So if we differentiate that function ER equal to minus delta V by delta r, so it was 2p cos theta by 4 pi epsilon naught 1 by r square was there. So if we differentiate it 1 upon r square, it will be minus 1 upon r cube, and negative sign will be positive. So it is the ER term, and E theta equal to minus 1 upon r delta V by delta theta. So in that case 2p cos theta will give us minus sin theta, so it will be positive, and 1 upon 4 pi epsilon naught p sin theta by r cube, because 1 r is already here and r square was there in last slide. So we can find out the electric field using the potential V. So this was all about the dipole, how we can find out the potential and electric field. So previous video was application of Gauss law for spherical, cylindrical and planar symmetries, and in next video I will discuss the Laplace and Poisson equations and the capacitors. So thanks for watching this video, and please subscribe this channel. Thank you very much.